for terminal count. 10.
Every space film should begin with a launch.
5, 4, 3, 2, 1, 0. We have ignition. We have a liftoff.
Because that's how space began. On the 16th of March, 1976, NASA celebrated the 50th anniversary of the first successful liquid-fueled rocket flight by Dr. Robert Goddard, itself a moment in time, only 23 years into the age of flight. This film commemorates the completion of a chapter, a most incredible period of scientific achievement. We humans are a restless breed, and the march of flight once begun has been swift. From the sands of Kitty Hawk, echoing some spectacularly unsuccessful predecessors, to Dr. Goddard's 1926 breakthrough, echoing some even more spectacular non-successes. Up through World War II, the Germans mounted a straight-up and sometimes straight-down effort. But the advances were profound in rocket guidance, in jet engines, and in the use of high-altitude balloons and sounding rockets to obtain our first tiny peak beyond the atmosphere of Earth. By 1958, America had a very good sounding rocket program and stepped with high hopes into
International Geophysical Year. The scientists tell us that they cannot possibly anticipate all of the valuable scientific knowledge that will result from their efforts. They believe that many of the facts thus acquired will give us new understanding and new power over the forces of nature.
How right he was, but not for the moment. Our ill-starred Vanguard program went to pieces, and right on television, so everyone could feel miserable. Meanwhile, back in the Ural Mountains, our Russian counterparts were preparing a small, unpleasant surprise. 184 pounds of bad news. A sign of enormous booster power at a time when our programs were still flying sideways and wrong ways. The civilian Vanguard program was basically sound, but just couldn't be accelerated. So when Sputnik 2 really set our national teeth on edge, Ike bit the bullet and gave a green light to the Army's Redstone under Wernher von Braun, whose team was later destined to carry us so smoothly to the moon. Vanguard's agonies had one important effect. They set the stage in Congress for the creation of a civilian space agency. Vanguard's weary but far from disillusioned teams of scientists and engineers moved intact to NASA and the NASA Delta Booster Program, located at one of the first NASA centers, Goddard, 15 miles northeast of Washington, D.C. Goddard was also given a NASA-wide mission for tracking and communications, serving all the other NASA centers. JPL for planetary probes, Kennedy for launches, Houston for manned flight, Marshall for vehicles, and Lewis, Ames, and Langley for aeronautics, where giant wind tunnels and experimental facilities served the continuing advance of safety and performance. With important breakthroughs in engine designs, fuel efficiency, exotic airfoil designs, improved construction, and in the understanding of the atmosphere and its effects. Just while the centers were getting started, the Delta rocket team stunned the nation with an unbroken string of 22 perfect missions in a row. Up they went. Weather satellites, energetic particle and radiation detectors, solar observatories, active communications experiments. In 4 short years, science gained a foothold above the reach of Earth's gravity and atmosphere, a position which began to really help us in our daily lives. Never again would a hurricane strike without warning. Through synchronous communication satellites, the world was brought closer together and knowledge was advanced. And in science, we were at last able to measure the ultraviolet and high-energy rays which are blocked by our blanket of air, giving us astonishing new information about the universe. Heavier rockets carried unmanned probes to Mars and the surface of the moon. but there were still many spirited disagreements about space. Could man survive weightlessness, cosmic rays, re-entry? Hardly any two scientists could agree on such basic questions as, could we land on the moon? Or would we just sink into it? By 1961, the spotlight was on manned flight, culminating in John Glenn's historic 3-orbit mission in February 1962. But once again, these great events were marred by the quick-footed Russians, who beat us into orbit by 10 months. Second place was last place, so even months before the Glenn flight, the nation welcomed a remarkable challenge to Congress from President Kennedy, asking that we put a man on the moon and return him safely to Earth within the decade.
Time for a great new American enterprise. Time for this nation to take a clearly leading role in space achievement, which in many ways may hold the key to our future on Earth.
With this stroke, mass science and mass invention were born. Tens of thousands of scientists, engineers, and technicians focusing on a monumental interdisciplinary effort towards a fixed goal within a fixed timetable. There were literally thousands of spaceflight questions to answer, problems to solve, flight items to design, engineer, and build. In every discipline, from flight dynamics to medicine to orbital mechanics, each was an assault on the state of the art. Each had to work 1,000 ways on the ground to be as certain as possible of its working in space. 8 years and 56 days after the goal was taken up, this dazzling display of teamwork and ingenuity did indeed propel us to a safe landing on another world, in the distinguished company of dozens of active science and application satellites, providing a strikingly beautiful and useful new view of Earth and the universe. For 5 years more, near-Earth space echoed with national and international achievements. School-teacher satellites, day and night cloud cover watches, space workshops, aids to navigation, search and rescue. By that day in March of '76, as the clock counted down to the 50-year milestone in the age of rocket flight, space research had really come of age. It was a joyful, if somewhat soggy occasion.
As we expand our island of knowledge, the boundary of the unknown grows ever longer. I like to compare our exploration efforts to those in the winning of the West. It's as if the Lewis and Clark expedition to the Pacific had reached its successful end, and the days of the great trek westward by Conestoga wagon are just ahead. In these tasks, we at Goddard will penetrate even further into the distances and mysteries of the universe and of Earth, but as usual, without most of us ever leaving our offices and laboratories.
Goddard Space Flight Center is a kaleidoscope of extremes, ranging all the way from a university campus to an industrial complex. It's a partnership of physicists, astronomers, mathematicians, engineers, managers, and experts in almost any high technology or craft you can think of, teamed together for the mastery of space. Each of its 25 buildings reveals a unique aspect of the vastness of this undertaking. In one, you will find the production lines for satellite output, the super sophisticated photographic laboratories which mass produce the satellite imagery, monitoring the health and condition of our planet on a day-to-day basis. Here, too, huge quantities of magnetic tape arrive from the worldwide tracking network for reduction and analysis. In other buildings nearby, you come across the space environment simulators and test facilities which have helped give us such high success with so many things that have never before been done. And in yet another building, you find the orbital computing and prediction facility, side by side with the worldwide voice and data switching centers which serve everything from manned flight to acquisition of signals from the far universe. Computers identify, address, and store or switch the enormous flow of traffic, much of it especially during manned flights on a real-time basis. Around the clock, whatever the weather, These buildings fill with the quiet, far-thinking men and women who are producing the ideas, systems, and hardware which is gradually changing our world and improving the overall quality of life on Earth. The Goddard mission begins with very human, current, pressing needs of two types. The first is the need for fundamental knowledge, the knowledge that comes from basic scientific inquiry.
We in the space sciences look from planet Earth to our solar system, to the far reaches of the universe. Instruments on spacecraft are the extension of our senses, ranging from radio waves to gamma rays. Our aim is to understand the forces of nature that shape man's environment.
In this enormous task, each investigator takes a small part of the responsibility within his scientific discipline. But that in itself can be awesome in scope.
My investigations indicate that there are volcanoes on the moon, which sometimes explode with such violence that they send small stones right down to the surface of the Earth. If we could have a satellite which would make a measurement of this part of the moon, then I think we might be able
In astronomy, well, the whole ball game is the universe. How it started, what it's like now, and where it's going in the future. We can solve these problems.
The detectors here are concerned with measuring gamma rays, which are like light waves, but are 10 million times as energetic. We even have certain sources which are emitting pulses of these gamma rays with amazing energies. Encouraged by these results, this even larger detector is being developed to look at the galaxy and the universe in great detail in this very high energy gamma ray region.
Some definitive evidence for the existence of neutron stars and some pretty conclusive evidence for the existence of black holes, but it's really only the beginning of what we hope to do in X-rays. In X-rays, we can see essentially out to the edge of the observable universe, and the experiments we expect to do during the next few years using big X-ray telescopes and space platforms are going to be able to tell us not only about X-ray sources in our own galaxy, but in other galaxies as well.
The second basic need which Goddard serves is the need for just plain everyday help, what we call applications. When will it be the best to plant? Is there a threat of a flood? What is the sea state east of Borneo? Is an earthquake coming? Can I get a call through to Tokyo now? Will the Olympics be telecast? Have they found the missing plane?
The efficient distribution of the world's food resources must be based on an up-to-date monitoring of the crop production in the world, in addition to the effect of adverse climatic conditions such as hail damage and floods. In addition, if we're going to improve crop production, we're going to have to monitor those areas which can be reclaimed and irrigated, and from that, improve crop production.
People living in and around the mountainous areas of the world know that snow provides the water they drink, helps to light their homes, and irrigate their crops. In order to know where snow like this is lying, we need satellite observations such as these to tell us where it is, and we're working on new sensors that will enable us to tell how much water is in that snow.
The weather that hits us during the course of a month comes from all over the world, and only a satellite will give us the data at low cost. And then we need computers to imitate nature with equations like this one that are solved in our machine downstairs and draw on the satellite measurements to tell us how the air masses will move. The two things together, satellites plus computers, will give us a true farmer's forecast in the course of the next several years if things work out well.
At the edge of Goddard's main site, there is a fully operational tracking station, which is part of the worldwide network and also serves for training. Tracking sites are positioned in Australia, Europe, South America, Hawaii, and Alaska to obtain complete coverage, especially of low-orbit satellites like Landsat and those used in manned missions. The workload is horrendous, and by the time the new tracking and data relay satellites go into action, the data flow will be equal to transmitting the contents of all the words defined in the largest dictionaries once every 3 seconds. Goddard also uses specially instrumented aircraft and ships to support split-second decisions over remote areas during the critical Earth orbit and re-entry phases of manned flight. But the most fascinating new development is the use of lasers in tracking. Skylab astronauts describe them as the brightest spots on Earth, and their accuracy is so great that satellites can detect a landmass shift of only inches spanning New York and California.
We may have some
Here in Goddard's Network Operations Control Center, the commands and predictions flow out and the data streams in. From this room, they manage the daily workload of up to 50 satellites, working in 6 nearly independent disciplines, 3 in science and 3 in applications. On that day in 1969, when we first landed on the moon, 132 science and application satellites had already been put to work. Today, the number exceeds 200.
If you're surprised at the number of spacecraft which have been put to work by Goddard alone, you may be even more impressed if you think of what it takes to design, build, test, and fly each single one. Every component, power supplies, attitude controls, sensors, and electronics, all must survive the test director's cleverest tortures. From the punishing vibration tests simulating the violence of heavy acceleration up through the Earth's ocean of air, to the massive anechoic chambers and vacuum chambers simulating the environment of outer space. The project team, the scientists, engineers, and managers must see that everything comes together on the launch pad, on time and with total reliability one day, several years in the future. The program may also have to survive frequent design upgrading as the multiple states of the art advance. Piece by piece, it all comes together in the surgical cleanliness of integration and final assembly, where again, they must prove that they all work separately and all work together well. Then, years down the line, the spacecraft builders bring their models and mock-ups to compatibility meetings with the rocket builders, usually Goddard's Delta rocket team, the rocket which has blasted more scientific satellites into orbit than all the other vehicles taken together. The moment of launch is thrilling and important, but the great moment, for those who have worked so long and so well, comes after a successful orbit, when the first commands are given, when the first cataract of data starts toward Earth, when it is successfully reduced, analyzed, and passed to the experimenters. Then, only then, all prayers are answered.
Here in Intralab, the Information Transfer Laboratory, Landsat imagery is brought down to Earth, brought down to the day-to-day needs and problems of managers and decision makers. People with a wide range of interests, urban planners, flood control engineers, and others, come here to work with us. They're here because of the great promise of Landsat technology for the operational requirements for information that they have. And they're here to learn, working with us, how to apply this new source of technology to meet their information needs. One example, working with forest management personnel, has been to determine and to identify computer-based techniques by which the Landsat data can be analyzed to give different yields of forest products and different types of trees in these areas. Each one of these picture elements represents about 1 acre of ground, which has been classified using winter and summer imagery. From this kind of product, we can distinguish hardwoods, recent and older clear-cut areas, areas that have changed from being vegetated to being clear-cut, and finally, areas of regeneration where pine trees have only recently been planted.
The more than 100 tons of instruments, sensors, cameras, relays, and telescopes which have been sent spinning so effortlessly about our Earth have touched us all. You can measure it. Long-distance calls are cheaper. The savings from increased accuracy and range in weather prediction is computed in billions. The cash benefits daily to shipping, farming, forestry, prospecting, control of pollution are readily acknowledged by those in the field. From basic science, even more dramatic applications will flow. Discoveries which will help us protect our near-space environment, increase our understanding of the mechanics of earthquakes, teach us how to relate the activities on our sun to events here on Earth. The next generation of effort will be based on multi-mission spacecraft carried on board the space shuttle of the 80s, making space research ever more accessible, more routine, and more cost-effective. It is everything that Dr. Goddard predicted, and more. How happy he would have been to join the 6 others riding that rocket into space with its vital payload of instruments and experiments. So ends our film, but not our story. You've seen the leap into space. You've seen the hopeful results of this new vantage point. You don't have to hold a degree in cosmology to know that the great next step will make the first one as pale as pre-Kitty Hawk.
I have here a copy of a letter written in 1932 by Dr. Goddard to the famous historian and futurist H.G. Wells. I think these words have a very special significance to us at this moment of rededication. For those of us who are looking back on 20 years of achievement in space, and for those of you youngsters here who may be responsible for carrying our dreams into the next generation, let me read just one paragraph for you. To me, this one paragraph says it all. How many years I shall be able to work on the problem, I do not know. I hope as long as I live. There can be no thought of finishing, for aiming at the stars, both literally and figuratively, is a problem to occupy generations. So that no matter how much progress one makes, there's always the thrill of just beginning.